Hey, Dr. Clark coming back at you with another preview video. This time we're looking at section 8.3, non-homogeneous linear systems. Let's take a look. So we've seen already homogeneous linear systems like this one, where you've got a vector y, maybe it's a x comma y, and then a matrix A, a 2x2 matrix times xy, or just written abstractly, the derivative of vector y equals matrix A times y. And we know how to find the homogeneous solution. We've done that before. But what we haven't done is a force system where you've got the linear system here plus some kind of forcing term, so that makes it non-homogeneous. And the question is, can we solve this? And the answer is yes, if we can find a particular solution. So because it's linear, we are able to use superposition. We're able to add a homogeneous solution with a particular solution to get the general solution. So the goal is, what is the particular solution? And as we've seen before, the trick is to just guess one that looks like the forcing term. So if the forcing term is constant, we might guess the particular solution to be constant, and that will oftentimes work. And if we can just figure out what constant it is, then you can basically solve the general system because we already know how to solve homogeneous. Okay, so that's the big idea for this section. It's really just taking something we knew already and then upgrading it to a linear system instead of just a regular linear differential equation. So the rest of the time I want to just look at a motivating example to give you an idea of where this kind of thing might show up. So let's take a coupled tank problem and model it as a system. We've got tanks A and B. They have 100 gallons of brine, so basically salt water, and they're well mixed, so there's some sort of mixer in here. But then you're pumping the water around, so you've got tank A or tank B pumps into tank A pumps into tank B. You've got pure water coming into tank A. You've got a mixture coming out of A, mixture coming out of B. And this is the interesting term right here, 1/2 pounds per gallon, 2 gallons per minute. So you're going to add 1 pound per minute of salt into tank B. And that is the non-homogeneous term. It's a forcing term of 1 pound per minute of salt, of new salt that's external to the system coming in. So that's your forcing term. And that's what we want to learn how to handle in this section. Okay, so how do you do that? Well, A of T denotes the salt in pounds in tank A. B of T denotes the salt in pounds in tank B. And then we're going to note the volume in each tank holds constant at 100 gallons. Why is that? Well, let's look at tank A. You've got 1, 2, 3. You got 3 gallons coming in, and then you've got 1, 2, 3 gallons going out. So 3 in, 3 out. So the volume stays constant. In tank B, you've got 2 in, 1 out, 3 out. So 4 in and 4 out. So that volume's going to hold constant as well. If the volume wasn't constant, technically you could still write down the system, but it would be much harder to solve. Okay, so let's keep going here. So we're going to now try to model it for A and B. So we need a differential equation for A and B, which is really just asking the question, how is the amount of salt in A and B changing? Well, let's take a look. In tank A, you've got pure water coming in, 2 gallons per minute. So that's 0 pounds per gallon, 2 gallons per minute. So that's a net 0 pounds of salt coming in. Then we've got B water coming into tank A at 1 gallon per minute. And there's B over 100 pounds per gallon. So B over 100 would be pounds per gallon times 1 gallon per minute. So this is pounds per minute as well. So that's a pounds per minute. And then A is leaving at, let's see, 1, 2, 3, right? So 1 out, 2 out, that's 3 out. So 3 gallons per minute, and then A over 100 is how many pounds per gallon? So pounds per gallon, gallons per minute. So 3A over 100, and it's negative because it's going out. That's tank A. So that's the only way that tank A changes hands in terms of salt. Now let's look at tank B. All right, so right here you've got a gallon coming out. So negative B over 100 times 1 because that's going out. Then you've got 1/2 pounds per gallon, 2 gallons per minute coming in. So that's 1/2 pounds per gallon, 2 gallons per minute. So that will end up being 1 pound per minute. Pounds per minute, right? Check the units. Then you've got salt coming in. A over 100 is how much pounds per gallon times 2 gallons per minute, so A over 100 times 2, and that's coming in, so it's positive. And then you've got 3 out again, B over 100 times 3, and we probably could even combine 3B over 100 with 1B over 100. That would be negative 4B over 100 if we just combine those two terms. So that's how you build your model. And you'll notice everything has an A or a B on it except for this term right here. That's a standalone term. So if we convert this system to a matrix vector problem, you end up with this system right here. You'll notice there's no forcing term on A, but there is a forcing term on B of 1. So the forcing term is 0, 1 for A and B. And then where's the other numbers coming from? Well, here's negative 3 over 100 here times A. So this vector times this matrix will give you negative 3 over 100A. And 1 over 100B, so there's 1 over 100B. Here we got 2 over 100A, so there's that. And then we've got, let's see, 4. 1, 2, 3, 4, negative 4 over 100 times B. So that's converting it into a matrix vector problem. And then, of course, the way you would solve this is you would ignore the forcing term, solve the homogeneous problem using the method of eigenvectors and eigenvalues to generate the homogeneous solution. And then since this is a constant forcing term, we would guess a constant for A and B, and then just have to solve that out for what number is A and what number is B, basically. All right. So that's essentially what this says here. Yeah, so finding the homogeneous solution, guessing a particular solution of this form, and adding the two to find the general solution. All right, and if you do that, there's really two ways to do it. First, you can stick it in a computer and run it numerically. And what you're going to see here is it appears that the solution is approaching some sort of equilibrium state right here. And if I had to guess, this looks like about 10, 30. Okay, so that's about 10, that's about 30. And you can see X, the amount of salt in tank A, is leveling off around 10, and Y, the amount of salt in tank B, is leveling off at 30. And that makes sense, right? You've got the salt is coming into tank B, but then some of the salt from B goes into A. So it probably makes sense that you'd have more salt in B than you would in A. You can also solve it exactly for an analytic solution, right? This is your homogeneous solution here. So if you find the eigenvectors of this matrix, it's this, and the eigenvalues are negative 1 over 20 and negative 1 over 50. So there's your homogeneous solution right there. And the particular solution, if we go back, finding C1 and C2, we're guessing it's a constant. That turns out to be true, and it is in fact 10, 30. And so there's your general solution right there. And you can see that these are transient terms here and here. So if we go back to the numerical, that's exactly what's happening. For some initial condition, this C1 and C2 are determined by the initial condition. And then over time, those transient terms burn off, and you reach the equilibrium state of 1030. Okay, so obviously we'll see more detail in class as to how do you actually do this, but this is the idea that we're going for. So hopefully you find that helpful, and we'll see you next time.